Let's explore how LEDs work and why they're becoming so popular these days. They come in various forms like bulbs or tube lights or even tiny LED lamps. And why are they replacing the traditional light bulbs? Well, LED stands for light emitting diode. And hopefully by now you understand what a diode is. A diode is a PN junction. And just to quickly recap, a PN junction is basically a P-type semiconductor and an N-type, a single crystal containing one side P-type, which has a lot of holes in it, another side N-type, which has a lot of free electrons in it. And there is a barrier in between, which we call the depletion regions, which does not allow the electrons and the holes to recombine with each other. But we've seen what happens if we were to apply a voltage to this. If we were to take our P side and connect it to the positive terminal, and we take the N side and connect it to the negative terminal and apply sufficient voltage, then the P side is going to push the holes towards the N type. The N side is the negative is going to push the electrons towards the P type. And as a result, now they will be able to overcome the barrier and they start diffusing and start recombining with each other. And as a result of this recombination, a continuous current starts flowing in this circuit. We call this the forward current or the forward biasing. Now, if you need more clarity on this PN junction and what this depletion region layer is and why recombination provides a forward current, then we've talked a lot about this in multiple videos on PN junctions. So feel free to go back and check that out. But anyways, that's what LEDs are. We have tiny diodes inside of them. And so if we were to, for example, open this up and look inside, you'll find these tiny rectangles. And when you pass current through them, they will glow. And that's how this entire bulb glows very brightly. But that's the question now. Why is it passing? Why is that when you pass the current, they start glowing? Well, that's because every time an electron recombines with a hole, it starts giving out light. But why does that happen? Well, let's look at this a little more carefully. We've already seen the band structure of a semiconductor solid. We know that it has a conduction band, high energy, where the electrons are free to move, and that's where the N-type electrons are in. And we have a valency band, lower level valency band, which is filled with electrons, but there are tiny spaces, which we call holes, and that's where the holes of P-type are in. And that means every time an electron recombines with a hole, the electrons fall through this band gap and go from a higher energy level to a lower energy level. And you might already know that when electrons jumps from high energy to low energy, that difference in the energy is carried away as a photon of light. And that's how every time there is a recombination happening, there is light being generated. Now, since most of the recombination happens near the junction, that's where most of the holes and electrons destroy each other by recombining, that's where most of the light gets generated or emitted, sorry. And this is how a light emitting diode works. So you forward bias it, electrons, holes recombine near the junction, giving out light. Now at this point, you may be wondering, you may be curious, hey, if that's the case, then shouldn't every diode give out light? Shouldn't my silicon diode also give out light? Well, yeah, it does, but remember, it need not give out visible light because visible light is a small part of the spectrum. You can get infrared light, you can get ultraviolet light. So yeah, all diodes when forward biased start giving you light, but not necessarily visible. And now you may be wondering, why doesn't silicon, for example, give us visible light? And which semiconductors do, and how do we build them? And what basically decides the frequency of light that comes out when electrons and holes recombine? Now, these are excellent questions which we'll tackle separately in another video where we'll look at why LEDs are not built using the regular silicon or germanium diodes, all of that in a future video. But for now that we understand the basic principle, let's quickly look at the advantages of LEDs over our more traditional light bulbs. First of all, they look at their size. Because they don't have to have a filament inside it, you can make them very tiny. And so you can have tiny LEDs which act like, say, indicator lights. And I'm pretty sure you may have seen them in your phones, in your laptops, and so many other devices. You can't do that with your normal bulbs. So they're very tiny and they can fit in any devices. So very tiny. Secondly, your traditional bulbs take a lot of electric power. Because you see, they have to first convert that electricity into heat, and then that heat gets converted into light. And so a lot of energy gets wasted as heat. Whereas over here, electricity gets pretty much directly converted into light because it's happening at the quantum level. There's no conversion of heat happening. And so it's a very efficient process. So it takes in, first of all, less power, and it's extremely efficient. So another big advantage, and that's why we are all moving towards now LED bulbs and LED lights, is because they are very efficient, much more efficient than the traditional light bulb. Another important thing is that your LEDs are extremely fast when it comes to switching on and switching off. For example, if I had a switch over here and I switched it on, then instantly the LED will turn on. If I switch it off, almost instantly the LED turns off. Very fast switching. But when you turn on your light bulb, it takes years to turn on. Okay, it doesn't take years, I'm exaggerating, but you know what I'm talking about. It takes considerable time to fully, to become fully bright. And then when you turn it off, again, it takes some time to cool down and finally for that glow to completely disappear. So LEDs are much faster when it comes to switching off and switching off, so fast switching. Now you may be thinking, why should I care about fast switching? Well, that is super important when you want to communicate using light. Let me give you a very common example that you might be familiar with, your TV remote. How do you think your remote communicates with the TV? The way it happens is there is a tiny bulb over here, and that's not a bulb, that's an LED. And every time you press a button, the LED switches on and off in a particular fashion. So pulses are sent to your TV. For example, let's say when you click this button, let's say this is our LED, what might happen is your LED might turn on and off like this. Something like this, some pattern like that. That pattern is sent to the TV, and that TV will recognize, that's why you press this button. If you press some other button, there'll be some another pattern that will be sent. So for every single button, there'll be a unique pattern that will be sent. And in order to send such a pattern, you need fast switching. Imagine there was a bulb which takes years to turn on and turn off. You can't expect to communicate using something like that with your TV. And of course, there are some other advantages as well. Turns out that LEDs can last a little longer compared to your traditional bulbs because they don't have to get heated up as much as your bulbs, and so more chances of them wearing out. Your LEDs also, if you think a little bit about it, because we are getting light at a quantum level due to electron transition, they're pretty much monochromatic. You can get single color of light. And again, something we'll talk about in a future video, but your traditional bulb will always pretty much give you white light.